Good morning, students. And now, in my today's class, we'll discuss the numericals further for vectors and other aspects of the vector fields, vector quantities. In the last class, we have just introduced the concept of vector calculations and how we can get the unit vector, directional derivative, the angle between the surfaces using the concept of gradient, and then in this class also we'll try to do the transformations, how to make the transformation from Cartesian to cylindrical or vice versa, or for spherical or cylindrical coordinates. Then we'll move ahead for the Stokes theorem and then divergence theorem. So few numericals will start, and let us see how much it can be beneficial, and all of you can take the maximum benefit out of this. So I'm just starting the class today. Just give me one moment. I hope you are seeing my screen. Yes. Okay. So as we discussed in my last class also, that we'll be going to discuss the numericals, and basically we are in the process of discussing the numericals on these topics. And myself, Dr. Pradeep Kumar Sharma from University of Engineering and Management, Jaipur. And in the if you see the entire syllabus of module 1, then there is vector calculus comprising of ordinary integrals, line integral, surface integral, volume, divergence, Stokes and Green's theorem in the plane. And then the second part of classical mechanics, having constrained motion, discrete and continuous systems, rigid and elastic bodies, degree of freedom, constraints, where we will discuss the constraints in holonomic and non-holonomic constraints. So first we are going to discuss, we have already discussed few parts of vector calculus, and now we are into the, you can say, the last phases of these discussions by discussing few numericals on these topics. And if you see the first part, already we have discussed a few numericals, but today I am going to start my discussion with this numerical. Calculate the differential volume to obtain the expression for volume of the. So what we will have to find? We have to find the differential volume first of all. Then we have to find the expression of the total volume of. There are three parts. Number one is sphere of radius b. So there is a sphere. We have to find the volume of that sphere. Okay. So first of all, we have to see what is the differential volume in case of a sphere. The second part says if there is a semi-spherical shell where the inner radius is a and the outer radius is b. And the third part, we have to find cylinder of radius b with height h. So that we need to start for this. We know that in a spherical coordinate system, because there is a complete sphere, already we have discussed in the class for these coordinate systems, for spherical coordinate system, there is this small differential volume dv is equal to r square sine theta dr d theta d phi. So there are three parameters, r, theta and phi. Okay. So if we need to find that value for, you can say, radius b, so r is equal to, r will have the limits from 0 to b for a sphere. The value will be 0 to b. But what is the value of theta and phi? So we have already learned that theta can take the value from 0 to pi. Okay, this is the plane. If you remember, and you can take reference of my last class on a spherical coordinate system. So this is the plane, and this plane can move entire for entire circulation, making a complete sphere. So that will be 0 to 2 pi. Okay. So these are the limits for three parameters: r, which can take 0 to b, theta, which can take 0 to pi, and phi, which can take 0 to 2 pi. So volume of the sphere, if we integrate this small differential element dv, so that is integral dv, but there are triple integration. First integration for the first parameter r, 0 to b, then theta 0 to pi, and phi 0 to 2 pi. But the value will be dv r square sine theta dr d theta d phi. So this way we can find it. R square dr with 0 to b, sine theta d theta with 0 to pi, and d phi with 0 to 2 pi. So we can easily find these values. Okay. So the final value is 2 pi put here. Then the value of sine theta is minus cos theta to 0 to pi. And the last one is r square. So we got these values, and you know the final result is 4 pi d cubed by 3. And all of you know that the sphere volume is 4 by 3 pi r cubed. But r value here is d. So the answer will be 4 by 3 pi d cubed. So this is the first part where we have found the value of volume of a sphere of radius b with the concept of our spherical coordinate system and triple volume. Okay, so that you can concentrate and practice more. Now the second part for semi-spherical shell, because the semi-spherical shell have two radiuses and it is half sphere. Okay, so it's not complete sphere. As you can see that over here the values will be, for r is equal to value will be from a to b, because inner sphere radius is a and outer sphere radius is b. So r value are changing from a to b. But for the value for dv, we need to find the theta and phi also. So we have theta is 0 to pi and phi is also 0 to pi, because you can see that r is from a to b, but theta, which is taking this value, complete value, it is intact as it is. But now it is not taking the entire circulation, it will take half the circulation. So if it takes the half circulation, it will have this semi-sphere in the z direction, like this, aligned. Okay, so we'll have these values here when the triple integration for the complete volume will be a to b for r, 0 to pi for theta, again 0 to pi for phi, and put r square sine theta dr d theta d phi. We'll solve this as we have done earlier in the same manner, and we got 2 pi by 3 b cubed minus a cubed. It's very obvious. But now we have used the concept of triple integration first of all, and the most importantly the concept of volume of differential element in spherical coordinate system, that we need to understand in a very simple and you can say important way. Now for the third part, where we find the value for differential volume for cylinder. If you can remember, and you can also take the reference of my class on cylindrical coordinate system, where we have found that the value for the small volume will be equal to r dr d phi dz. And this r is the radius of the cylinder, phi is the angle of that plane, right, and z is the height. So phi will take the rotation about z axis moving, or you can say the taking an angle, uh, this phi with x z. So accordingly it will move and will create a cylinder. So r dr d phi dz will be the small volume of this element. But there are certain limits. R can take the value 0 to b because it's given as per the question that radius of the cylinder is b. Z can take the value h because according to the question it is height h, but phi will take the rotation from 0 to 2 pi, making it a complete cylinder. You can find if you put the value phi is equal to 0 to pi, then you can find the half cylinder value. I think you can understand by changing the value of phi, you can easily find the half cylinder volume. But because it is the full cylinder, it is 0 to 2 pi. So we'll put the value in the triple integration to find the total volume of the cylinder, where the first is for R, A to B, second is for phi, second for height, 0 to h, third for this rotation, 0 to 2 pi. And we'll put the value for dV, R, dr, d phi, dz. Accordingly, it can be subtracted with the parameters 0 to b, r, dr, 0 to h, dz, and 0 to 2 pi, d phi. I think it can be solved in a very simple manner, and we all know that the volume of the cylinder is pi b square h or pi r square h, and we found the volume. But again, please remember, we have used here the concept of triple integration, number one, and we have used the concept of a small differential volume in cylindrical coordinate system. And anywhere where you can face means any environment is such that you need to find the volume in cylindrical environment where the source is aligned, then accordingly you can find. Then accordingly you can find the volume and you can use the differential things in a same manner. Okay, but you have to see and refer my discussion on the cylindrical coordinate system. Okay. Now moving to the next numerical, this very important numerical again on the triple integration part. You say for positive xyz, suppose there is rho is equal to 40 xyz coulomb per meter. Rho is the volume charge density, and because it is volume charge density, so its unit will be coulomb per meter cube, and the value is 40 xyz. We need to find the total charge within that region. So I think you can understand that there is a volume charge density, and if the volume charge density is given, we can find the total charge if we can know the volume. But the volume is given in the question with the regions. It is saying that you have to find the total charge within the region bounded by x is equal to 0 and y is equal to 0. But this relation holds good. 2x plus 3y should be in between 0 to 10 and z should be in between 0 to 2. So the region is given where the volume is available, and within that volume you have to find the total charge, and also the volume charge density is given in the question. But no, and then this task will be very easy to find. So total charge will be this. It is the triple integration and rho dV, and rho is 40 x y z, but the volume is triple integration x y z and dx dy dz. So we put the value for 0 to 5 for x 0 to y 0 to z, and you put the value for these limits from these conditions. The conditions are given that 2x plus 3y should be in between 0 to 10, and because y is 0 here, so x can take the value of 10 minus 2x by 3. So y is changing from 0 to 10 minus 2x by 3. Z is changing its value from 0 to 2. And if you put the y 0, then x value will be 0 to 5 according to this question, according to these conditions whatsoever given. So by using these conditions as given in the question, x0, y0, and these two main conditions, we can identify the limits for x, y, and z. Now we put the value and solve this equation in a very simple solution for integral calculation. Then we found that the total charge on, you can see the total charge in that volume given by these conditions, confined in this condition, is 925.926 coulombs. So this way, I hope you can understand that how you can use the concept of volume charge density to find the total charge. And you can easily use the concept of volume confined in any, you can say, any condition. The primary conditions are given as here in this question. Now, if we see the transformation part, there are 2 points. One point is given over here, that P in Cartesian coordinate system, we have to find it in cylindrical coordinate system. So, point P is there as 1, 2, 3. We have to transform this in the cylindrical system. And if you know, and you can refer my class on the Cartesian coordinate and cylindrical coordinate system or transformation, how to make the transformations. So you can understand that there is a point P in Cartesian x, y, z, but in the cylindrical system it is r, y, z. Okay, so we give x, y, and z values as given in the question, but rho phi z or r phi z is under root x square plus y square, phi is 10 inverse y by x, and z is equal to z, because in the high part there is no change in Cartesian and in cylindrical. So we can easily find the value for rho under root x square plus y square, phi as 10 inverse square 2 by 1, and z is equal to 3. So the point P, which is 1, 2, 3 in coordinate, we have transformed that point, the same point, in the cylindrical coordinate system as 2.236, 63.43 degree 3. Okay, so this is a very simple numerical of transformation. Now another numerical, we say that there is a point in the cylindrical system, 1, 45 degree, and 2, but we need to find its equivalent point in the Cartesian system. So you can understand it's the reverse of the last question we did. In the last question, we transformed from Cartesian to cylindrical, and here we are trying to do the reverse part, cylindrical to Cartesian. And we know that in cylindrical the value is given in rho, phi, and z. So rho value is 1, phi is 45 degree for the given question, z is 2. But we also know that if this cylinder point is there in the Cartesian coordinate, x, y, z values are easy to find as x is equal to rho cos phi, y is equal to rho sin phi, and z is equal to z. So we can find x is equal to 1 dot cos 45 at 0.707, y is equal to 0.707, and z is same as given, because in this part of cylindrical and Cartesian the height remains same. So this, the point in cylindrical system 1, 45 degree, and 2 is actually 0.707, 0.707 and 2 in Cartesian. So cylindrical to Cartesian transformation is, we can do like this. Okay. Now we need to find, and another numericals, important one, we need to find the constant m such that this vector, the given vector, phi vector, is solenoidal. Now what is the meaning of the solenoidal? If we can understand that what is solenoidal, then easily we can find this value. So you kindly refer the class on divergence. Okay. So the vector will be solenoidal if del dot phi is 0. It means if its divergence is 0, then the vector will be solenoidal. So we can find the value if we can put here in this equation that this del value and dot of this vector field, given vector. So I hope you all can do it in a very simple manner by solving this separately with x, with y and with z, and we got m is equal to -2. So this m is equal to -2 says that this, if we put in the given vector, the divergence of that vector will be 0. So accordingly this vector is known as solenoidal vector. Now verify the divergence theorem for the vector function. Now f is equal to 4xz I cap minus y square z plus y q. Taken over the q bounded by x is equal to 0, y is equal to 0, 1, z is equal to 0. So it's the condition given. So we have to prove the divergence theorem. Now what is divergence theorem? Divergence theorem says that if there is a surface integral of any vector field, so that can be equal to, or that should be equal to, the volume integral of the divergence of that vector field. So f dot n cap, because this n cap refers to the unit normal vector, if it is there, it should be equal to the total volume integral of divergence of that field. But the field is given here, if you can see, and the condition are given: x is equal to 0, 1, y is equal to 0, 1, z is equal to 0. So if we see this condition, because this is the q and boundary conditions are also given, its side is 1, so in all three directions the you can say stretch is 1 unit, 0 to 1 in x direction, 0 to 1 in y, and 1 unit in z. So we can identify the planes, and first of all we will try to find the values of these surfaces, because on the left hand side this is the surface integration. Now if we see the face 4, 5, 6, 1, if the 4, 5, 6, 1 is towards me, suppose this is the face, so we see the direction is n is equal to I cap in the x direction, positive x direction, and the value is x is equal to 1. So f dot n for the one part, the first, is 2. Okay, so we can easily solve it, and then it's 2. And for this, you can say the reverse of this surface is 1, 2, 3, 0 surface, and for this 1, 2, 3, 0 surface, f dot n ds for the second integration, second surface, is minus, because its direction will be opposite. So it will be 0. Now this 2, 5, 6, 1. So 2, 5, 6, 1 is in the direction of y, and its value is y is equal to 1. So f dot n ds, which is the third integration, is minus 1. And for 3074, which is the opposite of that 2561 surface, f dot n is 0. But for the face 2, 3, 4, 5, if you see the 2, 3, 4, 5 is the upper surface, pointing towards Z axis. So if we see this, so phase 2, 3, 4, 5, f dot n ds means is the fifth surface, the value is half. And for the reverse surface, which is the last surface of the cube, the sixth surface, f dot n, that will be 0. So all these values we can find by using the concept of this surface integral. So the total surface integral of the entire cube is sum of all, that will be 3 by 2. So on the left hand side of the divergence theorem, it says the surface integral of the vector field. So we have found the total value of that surface integral of the given vector field f for that cube. Now we have to find the divergence of that field. Now divergence is del dot f. So if we put the values, we can easily find the value of del dot f, that is 4z minus y. And we now will find the volume integral of this divergence using the limits of x, y, z from 0 to 1 for that cube. So we put the value, we solve it, and got the value of 3 by 2. So if we see on the left hand side, that is the surface integral already we found, and on the right hand side there's the volume integral of the divergence of that vector field, that is again same. So we have proved that divergence theorem is verified for this problem. So next numericals we will see in my next class, and I hope you can understand that these numericals are very important as far as the engineering physics is concerned, because in many of the environment and many of the applications of engineering, whatsoever the branch and whatsoever the subjects you are taking, but this environmental effect and environmental studies, environmental information, how to find the simple calculation of the vector fields spread in different environments of coordinates, you can say Cartesian, cylindrical, or spherical coordinates. That's very much important to understand for an engineer, where you have to work for the company, for any establishment of any factory. So you have to see that how you can use this knowledge. Okay, so we'll try to extend these classes of numericals on vectors up to next class also. See you soon. Thank you. Thanks a lot.